So welcome to another lecture in our video lecture series on the design of reinforced concrete structures. Today we will begin with second chapter of our lecture series and we will discuss primarily about limit state method of design today. So what are the contents of this chapter? First we will discuss on the safety and serviceability requirements. Then we will discuss on the design strength of materials and design loads. We will see the idealized stress-strain diagram of concrete and steel, and then we will discuss on some limit states related to both collapse and serviceability. So first, let me revise what is a limit state and what the method of limit state design involves. So when a structure or structural element becomes unfit for its intended use, it is said to have reached a limit state. As we discussed in our previous lecture, limit state is a state of impending failure. To reach a limit state means that a certain value has reached the limiting value. For example, if we are talking about the deflection of a beam and we say that the deflection parameter has reached the limit state, that means the allowable value of deflection is now exceeded by the actual value of deflection. That means we have reached an impending state of failure. We have reached a limit state. So the method of limit state design involves three main steps. First is the identification of all possible modes of failure. That is identification of the significant limit states. The second step is the determination of acceptable levels of safety against occurrence of each limit state. And this determination of acceptable levels of safety, these acceptable levels of safety is usually determined by a building code if we are using the design based on a certain code of practice. So it is the work of our building codes to define these acceptable levels of safety for each limit state. And after determining the acceptable level, the final step is the structural design for the significant limit states. So these three are the major steps involved in the design through the limit state process. Let's look at some ultimate limit states now. Ultimate, or you can also say them the safety limit state, correspond to the maximum load carrying capacity. So these limit state involves a structural collapse or part or all of the structure. So when the load carrying capacity of our structure is exceeded, then our structure tends towards a failure. So that behavior of our structure towards structural collapse. That structural collapse may either be of the whole structure or the whole building or only a part of our structure. So when our structure tends to collapse, then we say that the ultimate limit states or the safety limit states have been reached. Such a limit state should have a very low probability of occurrence because it may lead to loss of life and major financial issues. We already know that ultimate limit states are generally they are recognized or ultimate limit states. These steps are needed to be considered during the design process so that we can assure the safety of life of the people. So such limit states should have a very low probability of occurrence. If we look at some of these ultimate limit states, I have listed out 6 here. The loss of equilibrium, rupture, progressive collapse, formation of a plastic mechanism, instability or fatigue. And if you look at any standard building code, then you can see all of these limit states. There are considerations or there are design criteria relating to these limit states. The limiting values for many of these limit states. You can see these states or limit states being discussed in the building codes. So loss of equilibrium means the tipping or sliding of the entire structure, and this occurs if the reactions necessary for equilibrium cannot be developed. Rupture in our structural members or reinforced concrete member can occur either due to flexural or shear failure. Flexural failure means the failure in bending. Progressive collapse may occur when one overload or an overload on one member may cause it to fail. The load acting on it is transferred to the adjacent member which in turn may be overloaded and fail until a major part of the structure has collapsed. That means if we have a member here and for some reason this member is now overloaded and it is not able to resist the load coming onto it. So what happens is that this member fails because its load carrying capacity has been exceeded, and when this member fails, the load acting on this member is now transferred to another adjacent member. Now this second member becomes overloaded because excess amount of load has come onto it, and the load carrying capacity of this member is also exceeded, and consequently this member also fails. And due to its failure, now the total load coming onto this member is now transferred to another adjacent member in our structure. In this way, when the load has been, or when the members or the structural members have failed progressively until we can see that the major part of the structure has collapsed, that is known as the progressive collapse. Formation of a plastic mechanism. What is a plastic mechanism? Plastic mechanism is formed when the reinforcement yields to form plastic hinges at enough sections to make the structures unstable. Plastic hinges means if we have any structural member here and there is a plastic hinge here, if this represents a plastic hinge, then you can say that this plastic hinge, the member is able to rotate about this plastic hinge, and this plastic hinge does not carry any bending moment. So when your structure has enough plastic hinges formed in it, then that structure does not remain a structure but rather becomes a mechanism, and that mechanism makes the structure unstable. Another limit state can be instability. This instability can arise due to deformation of the structure. For example, buckling in columns may give rise to instability. And finally, this fatigue is another limit state, and which is caused in our structure due to the repeated stress cycles of service load. So these 6 are some of the ultimate limit states. After ultimate or safety limit states, let's come to this serviceability limit state. The serviceability limit state does not entail the collapse of our structure per se, but rather it involves the disruption of the functional use of the structure. So because there is less danger of loss of life, a higher probability of occurrence can generally be tolerated than in the case of an ultimate limit state. So serviceability limit state, since it is not directly linked with the collapse of our structure, these limit states are less linked, or these limit states are lesser a cause of loss of life. Rather, the primary thing that happens when these limit states are reached is that there is a disruption in the functional use of the structure. So because there is less danger of loss of life, we can tolerate a higher probability of occurrence for these limit states. So some serviceability limit states include excessive deflection, excessive crack width, and undesirable vibration. So what excessive deflection can cause? How does excessive deflection in our structure disrupt the functional use? Let's see here. This excessive deflection may cause machinery to malfunction. This excessive deflection may be visually unacceptable and may lead to damage to non-structural elements or to changes in the distribution of forces. We have given an example also here. For example, in the case of very flexible roof, deflection due to the weight of water on the roof may lead to increased depth of water. That increased depth of water may lead to increased deflection, and so on until the strength of the roof is exceeded. So because of this flexible roof, there is no initial danger to human life, or there is no initial collapse of the structure, but rather there is disruption in the use of our structure. And what happens is that as this deflection increases, then finally the strength of the roof may be exceeded and the roof may collapse. So this serviceability limit state is not directly linked to collapse or directly linked to the loss of life, but rather it is linked with the disruption in the use of the structure. So another serviceability limit state can be excessive crack width. It is possible to detail the reinforcement to minimize the crack width. Crack width are not bad per se because the reinforced concrete elements should crack in order to perform its function. But when those crack widths exceed the specified limits, then that may be unsightly for whoever sees those cracks, and those cracks may even allow leakage of water. And that leakage of water may even cause corrosion to the reinforcement, and as a result, there may be gradual deterioration of the concrete. And finally, undesirable vibration. These vertical vibrations of floor bridges and lateral and torsional vibration of tall buildings may disturb the users. So all of these limit states relating to serviceability are linked with the disruption in the functional use of the structure. So this is about some of the limit states, safety limit states and serviceability limit state. Now let's come to design strength of material and design loads. If you remember in our previous lecture, that is our lecture 1, we discussed on characteristic actions or loads and characteristic strength of materials. Now we discuss design strength of material and design loads. So what are the design loads? The design action or design load QD is arrived at by multiplying the characteristic action QC by partial safety factors gamma F, which is known as load factor. So you can see one general representation here. Characteristic action, which is QC, when multiplied by the partial safety factor and when summed up gives us the design load or design action. This summation here represents that the characteristic action may be of different types, and for each type of action there may be a separate load factor. For example, the load coming onto our building may be of different types: dead load, live load, and we can say another earthquake load, and also snow load, and etc. So let me write short forms here. For example, we use a safety factor of gamma 1 for dead load, gamma 2 for live load, gamma 3 for earthquake load, and gamma 4 for snow load. Now if we want to find the design loads, and if these sort DL, LL, EL and SL represent the characteristic load, our total design load is represented by gamma 1 into DL plus gamma 2 into LL plus gamma 3 into EL plus gamma 4 into SL. So this is how you determine the total design load. Gamma F is the partial safety factor for the load. So why do we need these partial safety factors? These partial safety factors are used in the determination of design loads because of the inherent variability in the determination of these loads. And how does this variability occur, or how does these uncertainties in the determination of design loads occur? For example, there may be the possibility of unfavorable deviation of the load from the characteristic values. For example, if we have considered that 4 kN per meter square is a characteristic value of live load acting on a roof of our building or any slab of our building, it may not be always 4 kN per meter square. The actual value of characteristic load may differ from this 4 kN per meter square, and it may become 4.5 kN per meter square. So to account for this deviation, we use partial safety factor. Possibility of inaccurate assessment of load also leads to the use of partial safety factor. Variation in dimensional accuracy, uncertainty in the assessment of effects of the load, and uncertainty in the assessment of the limit state being considered. So in one sentence, what you can say is that partial safety factors are used to account for the uncertainty or variability in the determination of characteristic loads. And to account for those uncertainties, whether they may be positive or negative, we use partial safety factors. So the value of this partial safety factor is given in table 18 of IS code 456. Remember, this is the code of practice that we will be using for this lecture series. So in IS code 456, in table 18 gives the values of various partial safety factor for loads, gamma F. So let's see in this table here. If we are considering a load combination of dead load plus IL means imposed load, then our partial safety factor for both dead load and imposed load will be 1.5. That means our design load combination will be 1.5 dead load plus 1.5 imposed load. Remember, we are now talking for limit state of collapse. For limit state of serviceability, you can see that all load factors used or all partial safety factors used are equal to 1 in this case. Similarly, if we consider a combination of dead load and wind load, we either use 1.5 dead load plus 1.5 wind load or 0.9 dead load plus 1.5 wind load. This is for limit state of collapse. Similarly, for serviceability, it is dead load plus wind load. Now, if you are using the combination of all of this, dead load plus imposed load plus wind load, a common partial safety factor of 1.2 is used. And for serviceability limit state, 1 times dead load plus 0.8 times imposed load plus 0.8 times wind load. So these are the values of partial safety factor for different load combinations. Look at notes here. While considering earthquake effects, substitute earthquake load for wind load. That means use the same partial safety factors given in these columns here, but instead of WL, use your earthquake load. Instead of WL or wind load, use your earthquake load. So this is about the value of partial safety factor of loads from which we get the design loads. So clause 36.3 of IS code talks about the design values. Similar to the design loads, the design strength of materials FD is given by this formula here. The design strength is given by the characteristic strength F divided by the partial safety factor appropriate to the material and the limit state being considered, that is gamma M. So this table 18 gives the value of gamma F, but to find the design values for the strength of materials, we use the partial safety factor gamma M, and gamma M value is given in this clause here, 36.4.2. Gamma M should be taken as 1.5 for concrete and 1.15 for steel. You can see that the partial safety factor for strength of concrete is greater than that for steel. It is because steel is manufactured in the factory itself, and under factory conditions, greater care can be taken for the proper manufacturing. So there are comparatively lesser constraints or lesser restraints, whatever you say, in the manufacture of steel. But this concrete is generally prepared in the site itself. We collect all the required ingredients and then prepare concrete in the site itself, so that there may be greater variability in the manufacture of concrete. So concrete has higher partial safety factor. Similarly, as we talked before, the design load is given by the product of characteristic load and the partial safety factor. So this is about the design strength of materials and design loads. Now let's look at the idealized stress strain diagram of concrete and steel. Now we are left with some topics. First, we will look at idealized stress strain diagram. Then we will look at the same for steel. Then we will talk about some assumptions that are used in the design for the limit state of collapse in flexure. This limit state of collapse in shear, torsion and compression, these will be discussed in the separate chapters, because we have to design for shear, we will learn about design for torsion, and we'll learn for design of compression members also. So we will only look at some assumptions related to the design for limit state of collapse in Flexure, limit state of collapse in compression. There are two more assumptions. And then we will look at some limit state of serviceability in deflection and then cracking. So for today's lecture, I will stop here. We have discussed till this design strength of materials and design loads. We will continue with our lecture in another video lecture series. We will continue with this chapter 2. So we'll meet again soon. Till then, stay safe and thank you.